Fast vector search is useless if the right candidates never enter the pool. Golden recall tests expose the misses query by query. This is the pattern you'll be able to implement by the end, which records golden queries and audits recall gaps. I'm Professor Pi, teaching search and IR with simple Python. Vector search feels fast and magical, but that speed hides a simple danger. If the candidate set never contains the true answer, no amount of ranking saves you. In real systems, that shows up as quiet failures. Users see plausible but wrong results, or important documents never surface. Golden recall tests give you a clear way to find those blind spots by comparing a trusted exact baseline to whatever fast path you actually ship. At heart, a golden recall test asks one practical question. For a small set of queries whose correct documents you already know, does your fast search return those documents inside its candidate window? If not, which queries failed and which gold documents were missed? That exact information is all you need to prioritize fixes. We'll build a short concrete pipeline, seed a tiny corpus, compute an exact baseline, simulate a lossy shortcut, report which queries lost gold documents, and then try a cheap re-rank to recover misses. It's compact, reproducible, and focused on the diagnostics you need. No full index rebuilds required. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we seed a tiny corpus and labels, so tests have something concrete to check. This snippet seeds normalized toy embeddings and gold labels to anchor subsequent recall checks. The array docs holds 4 short float triples built with NumPy's array constructor to represent document vectors. A twin queries array mirrors that structure, so each question vector lines up with the document space. Using np.linal.norm, both matrices are scaled to unit length, ensuring cosine similarity later reduces to plain dot products. The gold dictionary indexes which documents must appear per query, and the status flag confirms every vector now has unit norm, validating the printout. That exact baseline is useful but too slow at scale, so next we show a brute force scorer to lock down the reference recall. This example establishes a NumPy brute force scorer that locks in our reference recall. The exact top k function multiplies queries by docs.t to obtain cosine similarities and orders each row with np.argsort. The helper recall at k compresses those rankings into a mean recall, iterating through the gold targets and counting hits per query. Feeding k equals 2 returns the same top 2 neighbors we expect from the golden labels, producing a baseline free of ANN shortcuts. The printed exact recall at 2 shows every query currently retrieves the required documents, so the baseline accuracy is perfect. With a perfect baseline, we can simulate a common ANN shortcut or pruning. Here, I remove information and show what breaks. This snippet simulates an ANN shortcut by chopping each vector down to its first 2 dimensions. The truncated top k routine slices queries and docs to x2, computes similarities, and ranks candidates with NP argsort. Running it for k equals 2 exposes how removing the 3rd dimension reshuffles the neighbor order for the first query. We reuse recall at k to quantify the degradation, contrasting truncated recall with the earlier exact recall stored in memory. If you increase k, more candidates from the reduced space return, and the recall gap shrinks slightly, though the missing dimension still risks misses. The printed recall gap highlights that dimensional pruning silently drops part of a golden neighbor set, the classic failure we want to catch. Now that we know there is a gap, Engineers need a readable report that points to the offending queries and documents. This snippet turns the recall drop into a human-readable failure report keyed by document names. A concise doc titles list maps each document index to a mnemonic label ready for messaging. The failure report function walks through gold, compares truncated IDX with exact IDX at k equals 2, and uses list comprehensions to catalog missing labels. Whenever a miss occurs, it also records the exact baseline hits so engineers see what the system should have retrieved. Feeding the previously computed arrays surfaces the lone query where truncated search skipped spec intro. The printed counts confirm at least one golden document is missing and point to the specific label to investigate. Looking at misses, we can try a small targeted repair that keeps the fast path but re-ranks a modest shortlist using full vectors. This example re-ranks the truncated candidates with full NumPy scores to recover lost recall without rebuilding latency-critical pieces. The re-rank truncated function first reuses truncated top k to fetch a wider candidate k set and stores each query's shortlist. Inside the loop, it recomputes true cosine scores via queries kid at docs candidates t, trims back to final k, and appends results. The surrounding sum then compares re-ranked IDX with truncated IDX to count how many queries regained a required neighbor. Increasing candidate k explores more coarse candidates before re-ranking, often boosting recall while costing extra dot products. The printed metrics show recall snapping back to 1.00, while confirming exactly one failure was repaired by the re-rank stage. In a real system, you would map docs to titles, save failing query IDs, and surface these reports to an engineered dashboard. The same re-rank trick works as a lightweight rescue when rebuilds are expensive. To summarize, this test compares an exact brute force baseline to your fast candidate pipeline, so you can see which queries lose golden documents. Run it whenever you rely on approximations or prune vector dimensions and want to catch quiet errors. One caveat: your golden set has to be representative. A tiny or biased set will miss other kinds of failures. Next step: tune the candidate window size and re-rank shortlist. Try increasing the candidate K and measure how recall improves versus the extra dot products. If practical IR tutorials help your projects, subscribe and watch the rest of the IR videos.